definitely a much bigger garage than the one I started coding LoRa modulation in. I'm going to give a fairly technical talk today with two main parts. First, I will explain why Nicolas and I decided to use Chirp as the foundation of the LoRa modulation. And second, I'm going to explain a fairly simple scheme to predict collision, therefore to be able to predict capacity in LoRaWAN networks. So first, why Chirps? You all know that what we want with LoRaWAN is low cost, low power, and long range. The protocol itself is designed for low cost and low power, thanks to the absence of handover, the protocol overhead itself, which is very small. But I'm going to talk about the modulation itself. So why did you choose Chirp spread spectrum for the modulation? So if you want long range, you need to have low data rate. That's the laws of physics. And if you want low cost and low power, what you really want is simple radio reception. And possibly what you also want is a constant envelope transmission, which is going to improve a lot the efficiency of the power amplifier. But most importantly, what you need is a simple radio receiver and low data rate. What are the options for low data rate? We had the option from direct sequence spread spectrum, like we use in GPS. We had a choice of narrowband or ultra narrowband or frequency hopping spread spectrum. And we had a choice with Chirp spread spectrum. So why did we went with Chirp spread spectrum? That's because it's more simple to receive, and I will explain why. The most difficult part of the radio reception is the detection itself. It's to find the signal. We receive the signal below the noise. So finding the signal is like looking for something below the overall noise. It's very difficult. And there are two things you need to find the signal. It's frequency and it's timing. So with many other technologies like direct sequence spread spectrum, you need to find the right frequency of the signal and the right timing of the signal. That's a two-dimensional search, which, when you're doing that below the noise level, is very complex, very difficult. So the Chirp has the property of being only a one-dimensional search versus two-dimensional search, and I will explain why. So this starts to be a bit technical. You see here, there's the time and the frequency, and the Chirp is a linear wave whose frequency is varying linearly with time. In blue, I represent here the transmitted chirps, which we try to synchronize, and in red, I'm representing the reception chirp, which are what the receiver is trying to match. And what you see here is that there are different frequency offset and timing offset between the transmitter and the receiver. So this case, and this case, they are equivalent from the point of view of the receiver. Because what matters for the receiver is that the difference of the frequency between the transmitter and the receiver is constant. And you see here that these three cases have the same frequency shift in the end between transmitter and receiver. While the timing difference here there's no timing difference, and here there's a positive timing difference, is negative, while the timing difference is different. So several combinations of frequency and timing error yield the same result, which means that we're not searching in two dimensions anymore. We're not searching in frequency and time space, but we're only searching in frequency minus time, just this one dimension, which is here. So looking into two dimensions is much harder, which is why when you turn on a GPS receiver, it's going to search for minutes if there is no assistance before it catches the first satellite. With LoRa, because we are one-dimension search in this fancy frequency minus time domain, we can do that instantly. So this is basically the reason why it's much simpler to use Chirp spectrum than direct sequence or ultra narrowband. This translates into simple receiver on the end device side and also simpler gateways. So now now you know why we've chosen to use Chirps. The next part of the talk is about predicting collisions in a LoRaWAN network and about predicting capacity. That's really important if we want to scale networks, if we can predict the capacity. It's also important if you want to do roaming or if you want to do packet broker, because when you do packet broker, you're just putting networks together, collaborate. Therefore, you have more gateways, and the traffic is slightly different. You want to know what happens to the capacity. So probably you know that spreading factors, which are the different data rates, the LoRa modulation, the LoRaWAN can use, they are supposed to be orthogonal. So orthogonal, the definition of that is that they interfere each other no more than noise. So when you transmit at a certain data rate, if there is another data rate being received at the same time, it will impact no more than noise, the data rate you really want to receive. So it's really important that this property holds, because since we can receive below noise, if data rates act as noise to each other, it means that we can receive several data rates in parallel at the same time on the same channel. So that's really important for the scalability of the networks and the capacity of the networks. To formally prove that LoRaWAN capacity was strong, Semtech and MachineQ did a capacity trial last year, or maybe 18 months ago. We set it up 10 indoor gateways, 100 devices emulating thousands of devices, and sent and received 1 million frames to show whether the capacity was there. And of course, we proved that the capacity was there, because at the highest load, the success rate of this network was 97%. So the details of the network was 10 gateways receiving over 8 channels, and 4 data rates, 4 spreading factors, SF7, 8, 9, and 10, because it's in the US. And the rest of my talk is going to show that rather than setting up this network for real, we can just predict the result, which is 97% success at the highest load. So it's a way to much faster predict the capacity and the packet error rate, the quality of service of a network. So first, we're going to define an orthogonality matrix. So what is an orthogonality matrix? It expresses that when there is a time-on-air collision between two packets, when they overlap in time, sometimes one of the packets survives. So here, for instance, you're trying to receive SF9, so one data rate, and at the same time, there is an SF7 packet coming. This matrix, this 11%, expresses that, on average, the SF9 packet is going to be OK. Only 11% of the time will there be a deadfall collision. So the packet is not going to be received. Another example, so if SF9 is overlapped by SF9, the probability of missing the packet is much higher. That's because the same data rate is not orthogonal to the same data rate. So you see that it's pretty high on the diagonal and pretty low on the non-diagonal terms. This expresses how much free of interference the data rates are relatively to each other. How we compute this matrix is from the statistics of the signal levels. We know the distribution of the signal level. We know that a certain data rate requires, for instance, SF8 minus 10 dB, so 10 dB below the noise, SF8 can be received. And from the distribution of the relative power of different data rates, we can compute this orthogonality matrix. So that's the first step. But we're not there yet with the packet error rate. So again, this matrix expresses that when there is a time overlap, there is not always an error. So the next step is to compute the time overlap rates. We're going to multiply box per box the time overlap rate with the orthogonality matrix we had before, which is going to give us the packet error rate from the collisions. So how do we compute this one, the time overlap rates? So there is a very well-known formula for ALOA networks, meaning ALOA stands for random access networks. And this formula is the probability of time overlap is 1 minus the exponential of the load of the interferer times 1 plus the ratio of the time on air length, victim divided by interferer. So with this formula, we put here the length of an SF7 and SF8 interferer to compute this box, and etc. We know the load of each. We measure it on the network, and we compute this matrix. So it means that on this MachineQ Semtech trial, any SF10 packet, on average, was overlapped with an SF7 packet. So it's like 22% of the time, it was overlapped in time. But because SF10 and SF7 are almost completely orthogonal, this time overlap of 22% only translates in a 1% packet error rate for this collision case. So we do that for each box. So I'm taking another example. SF9 overlapped by SF9, so only 30% of the time, but because there is no orthogonality between them, it stays at 11.3% packet error rate because of SF9 being collided by SF9. Another example, SF7, 7% of the time is received at the same time than an SF10 frame, and the orthogonality is such that only 0.5% of the collision because of that. Then we can compute the total line by line, so 4.7 plus etc., which gives the overall packet error rate per spreading factor. You see that most come from the diagonal. Most of the impact comes from diagonal, and the non-diagonal terms are almost zero because of the spreading factor orthogonality in that case. So this is the packet error rate for the load we anticipated for one gateway, because 40.5% packet error rate is still pretty high. But hopefully, this network has redundancy, like in all LoRaWAN networks, because several gateways can receive the same message. And then we take this into account. So this is the diversity for different spreading factors of the gateways, but on average, 2.5 gateways receive the same packet. So when you take that into account, the probability of success rises to a level around 97%. So this is the predicted success rate from the formulas I just explained, and this is the measured success rate. And you can see that there is a pretty good match. I mean, it's only 1% error here, 0.8% error there. So we can very accurately predict the packet error rate, therefore the maximum capacity of such a network. So I'm going to recap the scheme, because I think it's really we had this question many times, how to predict the capacity. So I'm going to recap this scheme, which is pretty fast. So first, you need to measure or simulate the propagation and adaptive data rate, transmit power control, to gather the RSSI, the signal level statistics. From the signal level statistic, you will be able to compute an orthogonality matrix, meaning how bad is a collision on average. Then from the load, you will compute from the well-known ALOA formula the time overlap probabilities. Then from these two tables, you will multiply each box of the table to get the one gateway packet error rate. And last, from the redundancy, the average redundancy of the network, you will compute the network level packet error rate, which is also going to give you the maximum acceptable load for a given packet error. Therefore, it will give you the capacity. So instead of doing measurement, we can also do simulation. And the old way of doing simulation to predict capacity was to explicitly set packets here, there, in time, computing the attenuation from each packet to each of the gateway of the system, seeing if there are collisions in the time domain for these packets, and see which packets survive. So explicitly simulating packets, trying to send them and receive them, takes a lot of time. For instance, this curve here, which is the way I've done it, and you see it's not super smooth, meaning that probably more packets would be needed, takes a few hours on my computer to do. While this curve, the green one, which is using the model I just explained, takes like 1 second, and because it's not a simulation anymore, it's a computation using closed form formula. This curve shows that both methods give the same result, meaning that we can use the fast, simple way of computing packet error rate, of computing network capacity. Here I have written two curves, one with normal adaptive data rate, and the other one is with the worse adaptive data rate. Worse adaptive data rate here means that I take more margin in the assignation of data rates. For instance, it's like 6 dB more margin, so you would wait 6 dB more, so twice, 4 times the power of the received signal to decrease the spreading factor, to increase the data rate. So it's less efficient. Here on the left, that's the network simulation itself. Blue are the gateways, green are the endpoints, and each endpoint gets RSSI statistics and the number of gateways it's connected to. That's the only thing we derive from this. And then from the matrix computation, we get these curves. So really, this is a way we can do much faster simulation to derive the packet error rate, therefore the maximum acceptable capacity. So here you see that when you shoot for 10% packet error rate, you end up with around 80,000 messages per hour per gateway. That's a lot. That's probably a million messages a day per gateway. we can also use this kind of simulation, well, computation, to derive other consideration. So, and it is that repeating packet is a good thing as far as capacity is concerned. So this graph is, of course, collision rate, so packet error rate, versus the expected capacity, the number of messages per day. And imagine that we are trying to get a pretty high quality of service of 1% only packet error rate, so 99% QoS. If you're doing only single transmission, this curve will tell you that you need to be here, so 1% here, and 8,000 messages per hour per gateway. If you repeat once, transmit twice, it means that your single transmission packet error rate can be 10%, because 10% square becomes 1%. So 10% repeated once will give you 1% in the end. Then you're allowed 90,000 messages per hour per gateway, because, yeah, 10% square is 1%. If you repeat twice, of course, you should divide by 2 the number of messages to get the actual number of messages you're transmitting, the number of useful information. And this amount will be then 90,000 divided by 2, so 45,000. But you see that from a single repetition, you multiply by 7 the capacity of the network with the same quality of service. If you repeat twice, so triple transmission, or NB-trans equal 3 as a parameter of the LoRaWAN spec, you're allowed 22% collision rate, because 22% to the power of 3 will get you back to 1%. And here, your capacity will be 200,000, divided by 3, which is 66,000, so even 50% better than the previous case. So it shows that repetition provides an efficient replacement to systematic acknowledgement. It's really a good thing to do if you want to increase even your capacity. That's a bit counterintuitive, but that's what this simple scheme to predict packet error rate are good at. And with this, I am finished. So we have time, Chris, for maybe 1 or 2 questions. Hello.
Hello. I'm Fabien Ferrero from University Côte d'Azur. Thanks.
Hello, Fabien.
Thanks a lot for a very nice presentation. I would have a question about, have you an idea also in your study of the impact of the polarization, orientation of the device? Is it going to affect a lot the results?
So your question is about the impact of the orientation of the device.
Exactly. And then polarization.
So the answer, no, I haven't, but this scheme is capable of doing that, because at this stage, at the network propagation stage, then you can decide easily that the device has an attenuation of maybe 10 dB, constant toward all gateways, because there is a mismatch of the orientation. So in the simulator, which I will probably provide soon on the Semtech developer portal, there will be a parameter which will not be antenna mismatch, but it will be the attenuation losses. So it's like a random variable, and it will say that because of indoor, so maybe it's indoor and disorientation, misalignment, thank you, you will have between 10 and 20 dBs more attenuation. This will impact the statistics of the RSSI, therefore it will impact the adaptive data rate, the transmit power control algorithm, it will impact the orthogonality matrix, and then you will be able to compute if the slope is the same. But of course, if there is misalignment, the slope will be steeper, because you will use less, splitting factor 7, you will use more the low data rate, therefore you will have more packets, more collision. Well, longer packet, therefore more collision.
I'm sure that answered your question, right? Okay. Anyone else? Oh, hello.
Hello. So for the repetition, if you want to repeat a message to get a better density, do you want to send those 2 messages very shortly after each other, or wait a little time in between? What's the best practice?
Thank you. I understand. So is the recommendation to repeat shortly in time, or is it to wait? So the recommendation is to have channel diversity, so which is by default in LoRaWAN. Then if you repeat twice, so 3 times transmission, it doesn't really matter how long you wait, because you will have anyway frequency diversity between the channels. So what happens on one channel stays in that channel, and something else is going to happen on the next channel. While if you aim at repeating more than 8 times, if you start repeating many times for other reasons than capacity, then you'd better wait a little bit that the channel changes, because frequency is not going to offer you that amount of diversity. So few repetition, you don't care. LoRaWAN is going to handle that for you. More repetition, you should wait a little bit more.
Well, I have one. A very practical question. Olivier, at 2 o'clock you will return.
Yes.
Together with Francois and Nicolas, the 3 big inventors of LoRa. Panel discussion with Johan Stocking. So we have 4 techies together. It will be a very technical panel.
Well, we are not all technical. I mean, Francois invented the LoRaWAN market.
Ah,
you see?
Okay. So there'll be something in there for everybody.
He had a contribution. He had a technology contribution. We also had a market contribution, but you know, it was really BizDev was more important because we had to evangelize. Well, he had to evangelize and create, understand, pivots to be spotted on the market. We are seeing today.
Because you'll be talking about the past.
Yes.
The rocky start, but also about the future,
Of
right?
course.
The future of LoRa.
Sure.
Can you already say something about the future
Something about the future?
for LoRa?
Well, the future of LoRa is bright.
Or we'll leave it to this afternoon.
No, but a little bit of the future is unknown because we're living in the. It's a revolution. I mean, we are transforming the world. It's a digital transformation of the world. So it's going to happen. We know it's going to happen.
Yes.
And we'll have many surprises on which way it's going to happen.
Okay. We'll see you back here at 2. Thank you very much.
Thank
Olivier
you.
Seller.
Thanks.